Now let's apply Newton's law to solve our problem. First, we can use gravity law to replace all the gravity force by m times g. Let's copy all the equation we have. Here's all the equations. So whenever we see gravity, we can replace it by the mass of the object times the gravitational constant. We see that the mass, the gravity over here is acting on m1, so it's going to equal to m1 times g. So let me replace that. This is m1 times g. And here we have another gravity acting on m2, so we can replace that by m2g. Here we have gravity acting on m3, so we can replace that by m3g. Next, we apply Newton's third law. Newton's third law says that if I have two objects and they are interacting, let's say we have these two objects interacting, then the force they are acting on each other should have equal magnitude and opposite direction. In a vector notation, it means that the force should be equal to each other with a minus sign, indicating that the direction is opposite. And this force will be A by B and acting on B by A. Also, they might have different type of interactions between them, so the force need to be in the same type. So this is Newton's third law. But in our equation, what we're writing down over here is just the magnitude of the force, because we had already analyzed the direction of the force and write the direction in plus or negative signs. Therefore, what we want is to relate just the magnitude. When we take the magnitude, we'll see that the magnitude of A by B is the same as FB by A. So we can just say that the force A by B with the same type will have the same magnitude. So this will help us simplify our equation a lot. We see up here we have the friction force, and this is m1 by m2 and m2 by m1. So they form a pair. Let's copy everything down here to further analyze. The friction force from m2 acting on m1 can be paired up with the same type of force, which is friction, acting on m2 by m1. Similarly, the normal force acting on m1 by m2 can be paired up with the normal force acting on m2 by m1. These are the two pairs of Newton's third law pair in our equation. So we have them, and let's use the same mathematical designation, which is the same variable. Let's call this friction just a simple small f. So this equals this, and let's just call it f. Similarly, we can just call the normal force capital N. So these two should be the same, and let's just call it capital N. And then we can simplify our equation. This one will just be f. This one will just be n. And this one will just be f. And this one will just be n. Good. So now we can apply Newton's second law. to each of the components. Newton's second law says that F equals ma. In each component, it means that the x component equals the acceleration in the x direction, y equals y, z equals z, etc. And in our equation, we have all this stuff. And we want to look at our problem statement again, because we see that the blocks on the table are sliding only in the x direction, which means that the vertical acceleration should be 0. Y for 1 and ay for 2 should all be 0. Therefore, this net force for m1 in the y direction should be 0, and that for m2 should also be 0. We also have this one equals m1a 1x, but we know from our previous calculation we are going to name it just by a, so let's just write it as a. Similarly, m2 will have m2a, and for m3, because the negative of its y component will equals a, so this one will equal to negative m3a. So here are all the equations. We don't need the left hand side anymore. Let's copy paste it first. No, there's no more, so let's just get rid of the left hand side. Blah 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 blah. So we have the friction on m1 should equal to its mass times acceleration. Here we can tell how big is the normal force. This is the normal force. Here we can tell how big is the tension. We had already simplified the tension by capital T, so we can replace the tension over here with capital T, and same with this tension. So these are the 5 equations that we want to solve. These two will tell us how big is the normal force between m1 and m2 and the normal force of the table. This 3 is going to tell us the dynamic of the system, which is how big the acceleration will be. So we can first solve for the normal force. The normal force between the blocks will just be the weight of m1, while the normal force provided by the table should equal to n plus m2g, which is the total weight of the stack of blocks, which makes sense that the table need to give force that can support both of the blocks. Now we can solve for acceleration. Let's combine these two. The second one tells me that T equals m2a plus f. This is the second equation, so that I can plug it into the third equation and get m2a plus f minus m3g equals minus m3a. This came from the third equation. And then we can have that f equals m1 times a. Put it in here. We get that m2a plus m1a minus m3g equals minus m3a. Combine all the terms with a, here, here, and here. We get that the sum of all their mass times the acceleration equals the weight or the gravity force acting on the third block. This tells us the acceleration is just the weight on the third block divided by the total weight of the system. And this is a constant. So that if we look at the distance that the third block drops, it will be a constant acceleration motion started with zero initial velocity. So the displacement will just be 1/2 at squared. So we can just solve for the distance that it dropped by putting the acceleration we solved over here. The distance that it dropped will just be 1/2 this acceleration times t squared.